In this video, we're going to construct a lithium battery utilizing lithium ion phosphate or LiFePO4 cells. I'll guide you through straightforward steps to create your own reliable battery. The great news is the cost for materials have dropped significantly. You can now assemble a 280 amp hour 12-volt battery for under $500, including transport costs. By constructing your own battery, you gain the advantage of hand-picking quality components and configuring them to maximize space efficiency. This personalized approach contrasts with off-the-shelf commercial batteries, where the internals are often a mystery. Considering we're using similar, if not the same cells found in those commercial units, building it yourself bypasses the hefty markup for what essentially boils down to a branded plastic casing. Why pay a premium when you can craft something tailored and better for less? And it's so quick and easy to assemble. Let's first address the concerns surrounding lithium battery safety. Contrary to common fears, LiFePO4 cell technology is known for its stability and safety features. Unlike other lithium-based batteries, they are resistant to catching fire or undergoing thermal runaway, a hazardous condition you might have seen associated with lithium-ion batteries. While lithium-ion variants are commonly used in numerous devices, their higher energy density, which allows them to be compact, has been linked to safety incidents in consumer electronics like scooters, hoverboards, and even smartphones. That's why we're focusing on LiFePO4 cells. They offer a balance of energy efficiency and safety, and that's essential for peace of mind. Indeed, the safety of LiFePO4 cells have been demonstrated vividly online. There are numerous videos where enthusiasts test their durability in extreme ways by striking them with axes or drilling holes through them without the cells igniting or exploding. For me, the advent of lithium batteries represents one of the most significant technology leaps for the life of the grid. It's nothing short of a revolution. Lithium batteries boast incredible efficiency. Consider this: when a brand new lead-acid battery is charged from 100 amp hours of solar panels, it typically stores about 85 to 90 amp hours. And when it's time to use that energy, you might only get back 70 to 85 amp hours of usable power. Plus, as the battery ages, its capacity to store and release energy drops sharply. A few years down the line, that same battery might only give back 50 amp hours or less from the initial 100 amp hour charge. In contrast, a lithium battery can deliver approximately 95 amp hours or more of usable power from a 100 amp hour charge. Even when I was using high-quality AGM batteries, a persistent sense of being energy deficient led me to consider expanding my solar panel setup. However, once I transitioned to lithium batteries, the energy boost in my solar charging system was so remarkable that the idea of adding more panels became unnecessary. Previously, monitoring battery levels was a constant concern, but with lithium, it's almost a case of install and forget. The energy is just there when I need it. By the way, when I refer to lead-acid batteries, I'm including both AGM and gel types as well, since they all utilize lead-acid chemistry with variations in the form of the electrolyte. It's not just about efficiency, it's also about durability and cycle life. A lead-acid battery should ideally only be discharged to 50% of its state of charge to preserve its lifespan, offering around 700 cycles. In contrast, a lithium battery can safely be discharged down to almost 0% state of charge, with a documented cycle life of approximately 4,000 cycles. This difference is not just incremental, it's a huge leap that makes lithium the superior choice for long-term energy storage. For instance, let's look at the usable energy capacity. With a 300 amp hours of lead-acid batteries, you're effectively working with only 150 amp hours of usable energy, because you should only discharge them halfway. In contrast, an equivalent 300 amp hour lithium battery setup provides a whopping 270 amp hours of usable energy, as you can safely draw it down much closer to empty. This stark difference in usable capacity makes lithium batteries a game changer for energy storage solutions. So when you're upgrading, you could use a 300 amp hour lithium to replace 500 amp hours of lead acid. LiFePO4 batteries are approximately 30–40% more compact and lighter than their lead acid counterparts. For instance, a 500 amp hour lead acid battery bank might extend up to 1.6 meters in length, while a 300 amp hour LiFePO4 equivalent would roughly measure 33 centimeters in length. Here we have a lithium cell. I've selected these EVE amp hour cells for a few key reasons. First, they match the width of a standard battery, which means they'll fit seamlessly in my existing battery box. Plus, they're known for their solid construction and rigorous quality control, ensuring that we're building our battery with some of the best components on the market. Each cell provides 3.2 volts, so 4 of them are required to create a 12-volt battery. We also need a BMS, or battery management system. The BMS is the safeguard protecting lithium batteries from overcharging, undercharging, and operating extreme cold. While lead-acid batteries can often recover from severe discharging or overcharging, lithium batteries rely on the BMS to prevent damage from these conditions. I recommend opting for a smart BMS with Bluetooth connectivity. It allows convenient monitoring of your battery right from your phone. In a future video, we'll delve into how to integrate this BMS into our smart boat system using Home Assistant. I personally use a daily BMS. They are solidly built, have good diameter cables, and are easily mounted. And they look good. This one can handle 200 amps of continuous discharge. When purchasing these cells, they typically come with bus bars for interconnection. You might also find small plastic sheets to insulate between the cells. If they're not provided, you can improvise with thin plastic chopping boards, which work just as well. While in theory it's recommended to top balance your cells to ensure they all charge to the same voltage, I've found in practice that it's often unnecessary. If you source your cells from a high volume supplier, you'll likely find that they'll arrive with nearly identical voltage and state of charge. Additionally, due to transport regulations, cells are usually shipped with a state of charge of less than 30%, making it impractical to top charge them to 100% without specialized equipment. To initially set up your battery, simply connect your cells in series to form a 12-volt battery and use your standard charging sources like solar panels or alternator. Then keep an eye on the cell voltages through the BMS. If you notice significant discrepancies over time, you could consider top balancing. To top balance, you would charge all the cells in parallel until they reach 3.65 volts. However, many of us in the community, including myself and fellow enthusiasts, have successfully installed batteries without top balancing and observed that the cell voltages remain uniform. Should you ever need to top balance after initial use, you can then charge your cells to 100% state of charge with your standard setup, disconnect, and then top balance them using a small buck converter. All right, it's time to bring everything together. We're going to assemble the cells, hook up the BMS, and give life to our DIY lithium battery. So let's get started. Here we have the daily BMS. Now there are 3 ports we're going to have to use on this BMS, one for the battery sensors, the temperature, and the Bluetooth. There are 5 battery sense wires, common, and then 4 reds for the positive of each cell. If you look at the plug, it starts from the black is the common, and then the one next to black is cell number 1, 2, 3, 4. I've put ring terminals and labeled these wires just to make it a little bit easier. Now it plugs in, there's only one way this can plug in. Now the Bluetooth dongle, on the front of it has the Bluetooth ID and also has a button, small button to switch it on and off if required. The plug is asymmetrical, so there's really only one way you can plug it in, and it goes into the UART terminal. And I find just the last bit, it's just easy with a small screwdriver just to lever in gently, left, right. And then the temperature sense cable, it's just to protect the cells, because cells don't like to be charged when it's less than 0 degrees Celsius. You'll damage the cells. This goes into the NTC port, and again I just use my screwdriver to lever it in, and it's also asymmetrical as well, so there's only one way you can put this plug in. This is a 200 amp discharge model. You need to size your BMS based on your max power continuous draw, either your inverter or winch. Now the beauty of building your own battery, you're free to configure the cells to suit the space you have. So here I've put together 3 different configurations, how you can set out your cells. So I'm going to use configuration 1. So we'll put the cells here. You put them in alternating plus, minus, plus, minus. You can see it written on the terminals. Now I have these insulation boards, which I just put between the cells. It's just to stop them rubbing. Maybe they're not required, but I like them there. Let's check the cells before we use them to see their voltage. As I said, if you get them from a good supplier, they'll come with very similar voltages. So this is 3.32, 3.32, 3.32, and 3.32. These cells, they're about a year old, and I've never top balanced them, and the voltages are very similar. Here we have the bus bars, and so we're going to use configuration 1. So we put the bus bars as in the diagram. I'm using the bus bars that came with the cells. I find they're okay, but if you like, the beauty is you can choose whichever quality bus bar you want to put on here. So the BMS, just for this demonstration, I'm just going to lean it against the cells. So the first terminal we have to put on is the B- from the BMS, and also the black cell sensor cable. So we put them together onto the same negative terminal of cell 1. And then we go through the 4 positive small sensor wires, and we put them under the positive cells of cell 1, 2, 3, and 4. Now I've got the BMS just leaning against the cells here, but on my boat I have it next to the cells, and I've got it screwed into the wooden battery box. These BMSs, the dailies, come with little screw holes to mount them. I like it much better than you see people just taping it to the side of the battery. You don't need to do that. It's much better to mount it securely somewhere. So we're up to the 3rd sense wire. So this senses the voltages for each cell, and you can see that through the app. The last terminal, we're going to use the positive cable with the number 4 sense cable. The positive cable, it's better you don't have it connected to a load or discharge, have it disconnected. And then we have 3 more nuts we have to put on. Again, the nuts I'm using are the ones that came with it. They have a serrated bottom to stop them slipping, but again, you're free to upgrade the nuts if you want to use different quality or better quality nuts. This is the beauty of building your own. You can put in whatever components you like. Now we just have to go through and tighten each of these. Now tighten them firm, but don't go too hard, because these are usually just welded onto the cell, so you could break them with too much force. When you do your installation, these sense wires, you can put them with small cable ties and put them nicely. Okay, so let's now check the total voltage. The 4 cells have been put into series, so they should be they're a 12-volt battery now. So we'll connect the multimeter to the negative and to the end of the positive cable, and we get 13.3 volts. Pretty good, so it's actually functioning. There are rare cases that the BMS isn't activated and it will show 0 volts. So you need to then put a charge or a load onto the positive negative, and that sort of wakes up the BMS. And that's it. We've built the LiFePO4 battery. Watch this video for an innovative way to easily connect this battery to the rest of your system. So for the daily BMS, they have an app called Smart BMS. Let's go in here, local monitoring. Now you need to set these up as parallel, because it's actually saying you're going to have a number of different LiFePO4 batteries that are in parallel. It's not looking at the cells. Then you have to select your Bluetooth dongle device. It's the same number here that you have on the dongle. And then you click on it to go into the configuration. Now let's just check a few things. That the sum voltage is what we measured, which is 13.3. And importantly, the temperature, it's showing the correct temperature for where you are. And then the 4 cell voltages, just make sure they're more or less what we measured before. So here we on this page, we set the high voltage disconnect and the low voltage disconnect. I've set 14 volts and 12 volts. It's quite conservative. And you also set the maximum discharge and charging parameters. My BMS can discharge at continuous of 200 amps, but it can only charge at 100 amps. So I need to update this with 100 amps. So put in 100, click set, and ask for your password. The default daily password is a great number, 123456. So on the cell characteristics page, we need to set the type of the batteries, LiFePO4, the rated capacity. I put 250, it's a little bit less. I'm quite conservative with my cutoffs. And we also need to set the state of charge. Usually the batteries come at 30% state of charge, but I put 50 here. It's important to set the cell voltage to 3.2 volts as we're working with EU 3.2 volt cells. So the temperature, we need to make sure we put the low temperature of close to 0. I put 2 degrees Celsius, so we'll stop charging if it's at 2 degrees Celsius. And the last page, you can actually switch off. It's got virtual switches to stop charging or discharging of the BMS, which is quite useful. So you can see that on the front display, it's set the state of charge to 50%. Once we charge it all the way up, it will trigger the high voltage disconnect. It will then automatically set the state of charge to 100% and it'll be more accurate. But you've got to take the state of charge with a bit of grain of salt. Most of these BMSs, they're close, but they're not 100% accurate.